that I am still trying to understand them. But I think for a good part of it, for say to maybe number four now, for example, I mean say number seven rather, say to number seven, I think I know them. Then probably for eight, I have an idea of the definition and nine. But from that 10 upwards, a good number of it are diagrams and explanations and the likes. I have downloaded like a material that I'm going to use, but I've not been able to like break them down to understand them sharp. But so I will do the explanations of the one I know. Then yeah, so um, I think the rest would probably figure it out. So this is also to help us rejuggle our brain too, because I think a good number of what I'll probably be explaining, I've already like we did for those that were in class the day we did like before the test. Before the test, I tried to do an explanation. So I'm thinking that that explanation too would also surface here, or it's just going to help us rejuggle our brain. And yeah, and I'm hoping that that will help us in our exams. So the questions, let me see how I can do this. Okay, let me split. Okay, yeah. So the questions, the first question is for the one we are told to. For question one, we are told to explain the following with we are told to explain it with truth table and its circuit diagram where needed. So the first one is logic gates. So logic gates basically does not have like a diagram in that sense because every of these things that is mentioned there, the OR gates, AND gates, and the likes, they are all logic gates. So logic gates is like the umbrella name for all of them. So basically, logic gates is like the building block of digital circuits, and they perform Boolean operation on one or more inputs to produce a single output. So just basic understanding, it's the basic building block of digital circuits, and they perform Boolean operation of one or more inputs, where there are one or more inputs to give out a singular output. So logic gates gives out, they take in multiple inputs. It can be one input or multiple inputs to give out a single output. So I think that's the basic thing you need to know about logic gates. So the core thing is it's the basic building block of digital circuits. Uh, Let me see how I can produce this thing of digital circuits that performs Boolean operation on one or more binary inputs to produce single output rather, binary, to produce single output. So that is what logic gate is, and an example of logic gates can be AND gates, OR gates, and the likes. So that is number one. For number two, so since we are told to explain it using a truth table or circuit diagram, so for OR gates, so an OR gate is a Boolean operation where like it's a digital circuit where um, it turns positive, that is, it turns true when either
Daniel,
can you hear me?
Daniel, go on.
Yes, when either of the inputs is one. So that is for all gates. So the diagram for all gates is this. So this is diagram for all gates. This is an all gate. And let's say we have, so say we have an input, trying to write the input now. Input A and B here, and input B here. So our output Q will be equals to A plus B. So the truth table for this is A, B, and Q. So 0, 0, 0, 1, 1, 0, 1, 1. So for this, both are 0. So this is going to be a 0. You know, for all gates, it only needs one of the inputs to be 1 before we have a 1. So one of it is 1, which is the B. So it's going to give a 1. This one too, A is 1, so this is going to give a 1. Both parties are 1, so this is going to give a 1. So this is the this is an OR gate. This is what an OR gate looks like. So the second one is AND gate. For AND gate, it needs both inputs to be 1 before it can give an output of 1. So both inputs need to be 1 before it gives an output of 1. So this is an AND gate. So this is an AND gate. For the Q would be A dot B. The Q will be A dot B. Then this now would be, so both outputs are 0. This is going to be 0. Only one output is only output is 1. This is going to be 0. This is also going to be 0. Then this will be 1 because it needs two of the inputs to be 1 before it can turn 1. So that is for AND gates. Then the third one is XOR. Can you please mute your mic, please? Okay, thank you. So for XOR gates, XOR is exclusive OR gates. So exclusive OR gate is exclusively OR. That is, it must only be one input, like one of the two inputs that must be 1. That is, it is exclusively OR. It does not need both inputs to be 1 or to be on before it gives an, I mean, it only needs one of the, like either parties, just one of the inputs before it turns 1. So uh, so for this, for exclusively for the diagram would be uh, this is going to be the diagram. But here would be give me space here. So because it's an exclusive or yeah. So there's a circle. So that's A exclusive B. So the truth table will be this will be zero. This will be one because it needs just one. This will be one and this will be zero because it only needs either of the it only needs one of the inputs to be one. It does not need both of the inputs to be one before it is one. So that is for X or exclusively or. So the next one is a bubbled gate. So bubble gates are basically like an alternative gate that can be used in the place of like the original gate, and they have a bubble. Like that's like the simplest explanation. So bubble gates are gates that has a bubble either at the inputs or at the outputs, and they are used um, in place of the original. They still give like the same. They still give the same output, but they are used in place of in place of the original gates if the original gate is not available. So for bubble gates, I think it's only the diagram that will surface for bubble gates. So let me see. So let's say, for example, I think from class, I explained that say we have an AND gate now, for example, the bubble gate of this, which will still give like the same results to this, will be something like this, would be a so it will be a representation of bubble anywhere there is no bubble, and it will be the inversion of this. So this is an AND gate. It means what we will have will now be an OR gate. Let me see. Can this draw an OR gate? I'm trying to draw an OR gate. Don't mind the drawing. So there will be a bubble here. There will be a bubble here, and then there will be a bubble outside here. Then uh, this. So this is a typical example of this is a typical example of a bubbled gate. So um, this is a bubbled OR gate. Yes, this is a bubbled OR gate. So that's the explanation for bubbled gates. Then for NOR gates, so NOR gate is basically the inversion of OR gates. So it's an OR gate with a bubble in front of it. So this is the NOR gate. So NOR gate is basically not OR. That's like the explanation of a NOR gate. That is, it is not OR. It is not an OR gate. The negation of OR gates, basically. So I think this is big. So this would be the complement of this. So the truth table The truth table of this would be, so instead of what we had for all gates, it will be the negative of that. That is, wherever there is zero, it is now going to turn one. So it means this would be one, this would be zero, this would be zero, and this would be zero, because all of these are one in OR gate. So NOR gate is the negation of an OR gate. Did we get that? Did we get the explanation of all of this? So that is number one. So for number two, I mean for number one B is explanation combinational of combinational logic. So the explanation for combinational logic is that it is um it is a logic circuit that the input depends, I mean, the output solely depends on the input and it has no memory. Like that's the basic, it's a logic circuit whose input, whose output is solely dependent on the current combination of the inputs. So an example, so it doesn't have a memory or feedback. So the output would always change immediately there is a new input. Anytime there is a new input, for example, if there are, let's take this as input and output now, the result we will have here will be dependent on what we have here. That's basically like explanation for combination circuit. So anytime this input changes, it will also change whatever we have in the output because there is no memory to take in whatever we have, like whatever results that we've had before. So that is what a combinational logic circuit is. So, and an example of combinational logic circuits are multiplexers, decoder, encoder, subtractors, and others. Others, subtractors, multiplexer, encoder, and decoders, they are examples of combinational logic circuits. So for full adder, so a full adder is a type of combinational logic circuit that adds three inputs and produces two inputs. So let me type this uh, 1B. So 1B combinational circuits. So basic logic circuits with outputs solely dependent on the input, on the current combination of the inputs. Yeah, on the current combination of inputs. It has no memory or feedback. I think that's like the basic picture. So examples are adders, multiplexers, encoders, decoders. So full adder type of combinational logic circuit that has three inputs and uh, produces two outputs. And the inputs are, so the drawing for a full adder is something like this: three inputs, then to output. So the inputs are so the inputs A, B, and then a carry in, basically like C in. So these are the inputs. And on the output side, it gives out sum and carry out. Sum and carry out. So that's just a C out. So that's for full adder. For a subtractor, so half subtractors is subtract one bit of input from another. It subtract one bit of input B from another input A and producing a difference and a borrow. So half subtractor subtracts input B rather. So this is um this is half subtractor. So the difference coming is represented as A plus B, and then the borrow is represented as A bar B. So um, that is a subtractor. Then the next question two. Did we understand this, please? Did you understand everything in question one before I move on? So if I'm not getting a response, I'm taking that we already understand that. Any question? Okay, good. So for question two is we are to derive the Boolean expression. So and from this diagram already, we can see AB combining with CDE. And from what we already have, like what we've done here, this is what AB is. Then the other components are AND gates. So AB is OR gates. So the answer to this would be A plus B. A plus B, then ANDed by C, then ANDed by D, ANDed by E. So this is the Boolean expression from this logic. A plus B, which is OR gates, and OR gate is represented as A plus B. Then AND is whatever component it is dot the other input. And so this would mean A plus B dot C and then all of this also dot D, then all of this also dot E. So that is number 2A. 2A. So 2A, 2AII is we are told to convert the decimal numbers. So we are told to convert decimal AB60, B16. What's that subscript? Let me just take this as B16. Should be able to write subscript. I was thinking there's a way to write subscripts, but take this as a subscript 16. So to do this, what you just have to do is to add a zero, like trying to see how I can do this without this thing conflicting the other. So what you want to do is to, let me just write them, is to do a zero, so a zero, one, two, and three. Then remember that it's already in base 16. So that would mean this would be equals to a times 16 raised to power 16 raised to power 3 plus b times 16 raised to power 2 raised to power 2, then plus 6 times 16 raised to power 1. Then this would, the last one will basically be 0 because that would be 0 times 16 raised to power 0. So A is 10, A is 10, B is 11. So A is 10. We are probably going to see what makes A 10 later on by the time we are doing the other. So A is 10. So that would be 10 times 16 raised to power 3. So that's 16 times 16 times 16. That's 4,000, 4,096. So that's 10 times 4,096 plus B is 11. 11 times 16 times 2. 16 times 2 is 256. 256 plus 6 times 16. So I'm thinking that you should be able to like get your results here. You should be able to get your results here. This would give the total of everything is 43,872. I think. Yeah, the total of everything is for 3,872. So the same process for the second one. I is 6421 base 8. So that will be, so if you put 0, 1, 2, 3, that will be 6 times 8 because it's base 8 here. 6 times 8 raised to power 3 plus 4 times 8 raised to power 2 plus 2 times 8 raised to power 1, then plus 1 times 8 raised to power 0. So this would be 8 times 3 is 8 times 3. Sorry. 8 times 3 is 24. So that's 6 times 24. 6 times 24 plus 4 times 16. 8 times 2 plus 2 times 8, which is 16. Oh, sorry. 8 raised to power 8 raised to power 2 is 64. Yeah, 4 times 64 plus 16, then plus 8 raised to power 0 is 1, and the other one is 1. So you get your results from this place. I believe we can get our result ourselves for that one. So this part for 2B, we are told to convert the unsigned binary into octa and hexadecimal. So the A part is 0.1010. So for the octadecimal, know that you are, so for the octa, why am I making mistakes? For the octadecimal, you would want to separate the numbers in threes. So for the numbers after decimal, it will now be 101 space 000. That is in arrangement of three. So then you have your results. Then for the hexadecimal, it is in place of 4. So you divide it into 4 each. So this is going to be 0101, then 0000. So to get your hexadecimal. So before we do this, let's just do let's write all the decimal, like let's represent all the numbers in decimal and hexadecimal. So 0 is 0 and it's 0. As a shape like this. Okay. 0 0 0. Okay, yeah. So 1 is 1. 1 is 1. 1. So 2 is represented as 1 0 in binary. 1 0. So this is 2, 3. 3 is 1 1. And 4 is 1 0 0. 5 is 0 1 0 1. 6 is 1 1 0. 7 is 1 1 1. 8 is 1 0 0 0. Then 9 is 1 1 0 0 1. 10 is 1 0 1 0. And this is where we now start A. 11 is 1 0 1 1, which is B. 12 is 1 1 0 0, which is C. 13 1 1 0 1, D. 14 1 1 1 0, which is E. 15 1 1 1 1 1, which is F. Yes. So this is our representation. So let me just move this to this side. So the reason I'm writing this is so that it will be easier to easily represent all of this. So 101 is 5. So this is going to be 50 octadecimal. So that will be 50 base 8 because it is octadecimal. So you want to that will be 0 point rather. There's a point 0 point 0.50 coming. Give me a few minutes to plug my laptop. Okay, so that's 0.50 base 8. So you want to put a base 8 on that. Don't forget that. 0 points. This is 1010. 1010 is 10, which is the same thing as A. So you are not going to write it as 10, you are going to write it as A. So this is A base 0 point A base 16. You must not forget that. So for the B is 101100. So for octal representation, you divide in three. So when you were separating dots, you separate in this direction. But when you are separating whole number that is not decimal, you separate in this direction. So remember that when it is this, you are separating in this direction, but when it is that, you are separating in the other direction. So the octal of this is now going to be um, is going to be 0, 0, 1, 1, 0, 1. So that's going to be the octal of this. So it means the hexa, okay, it means the hexa of this would now be the hexa of this would be in fours 1, 2, 3, 4. So that would be 0, 0, 1, 0, 1, 1, 0, 0. So that is the hexa of this, that is splitting into 4. So it means this is equals to 5. 101 is 5. Then 100 is 4. So that's 54 base 8. And this would be equals to this is 2. 00102 and 1100 is C, 12C base 16. So let me just do one more example. Let me do the example E. So E is 11101.01. So the octal of this would be equals to uh, 33. So that would be 011.101.010. So in separation of 3, the hexa of this will be 124. So 0001 1101 then dot 0100. So the octa, it means this is the same as 11. 011 is 3, 101 is 5, then dot 0102. So that is 35.2 base 8. Please remember to put the base for octa and hexa, please. Then for hexa, this is 1 and 1101. 1101 is D, 13. 13 dot 1D dot 0100 is 4, base 16. So I think we can do this. We can do this ourselves. Like we can do the remaining ones ourselves. So that is how to group signed and I mean that's how to group binary numbers into octadecimal and hexadecimal. So I'm hoping there's no question on that. Any question?
Yeah, I have a question, please.
Okay.
So you say when it is decimal, we are going to
Yes.
count it to the right hand side, right?
You are counting here to the right, yes.
And but this last one you just did now, you count to the left now.
It's to the right.
Because you started from look at the octa. It says 0 0 1 1 1 0 1.
Yeah, so it's splitting
Then
into
zero
three.
one one.
So it's
Yeah,
splitting
I
into
thought
three.
you
So the
you need
remaining
to
of
count
this it
to
will
the
be
right.
0 0 0.
And but why do you start with 0 1 1?
0 1 1.
If you are count, yeah, the
Yeah,
octa.
that's
I'm
the
talking about the
okay, the
octa.
octa. So if you count from this place now, this will be one, two, two, three, right? So it's going to this is
And
the
that
first
is
one.
the you are counting to the left now, but you say it's supposed to be right. I didn't get. I didn't understand it
No,
well.
I said that for decimal, this is a combination of whole number and decimal. So this is the whole
Okay,
number part, this is the whole number
okay,
part,
okay,
and then this is the decimal part. So this is a combination of decimal and whole number. So for the decimal part, is the decimal part that you are counting to this side, to the
okay,
right side, yes, and the whole number you are counting to the left. So this
okay,
is a
okay.
combination of the two.
D2. Okay,
Yes, it's a combination of the two.
okay. I get it now. Thank you very much.
Yeah. Any other question, please? So that's number two. I'm guessing that we understand that. So for number three, we are told to so simplify the following SOP expression, which came K naught map process. So K naught map is a graphical representation of calculation of simplifying this Boolean algebra. So we have x equals to a bar b c d plus a b bar c bar d, then plus a bar uh, a bar b bar c bar d, then plus I've done three, one, two, three, a b c bar d, then plus A, B, C bar, D bar, then plus A, B, C, D. Okay. So we have this is the expression that we want to use K-map to solve. So to make it easier for you, for me, this is the way I did it. So I'm just going to copy each one, this one now. So the first one, the second one, third one, the fourth one. I think it's better writing it. D. Then A, B, C bar, D bar, then A, B, C, D. So now representing this now would be anything that has bar is zero. So this would be 0 1 0 1. Then this should be 1 0 0 1. Then this should be 0 0 0 1. Then this should be 1 1 0 1. This should be 1 1 0 0, and this should be 1 1 1 1. So now to draw K-map, so K-map is going to be something like this. So K-map is going to be something like this. So we have our AB in this side, AB, and then we have our CD on this side. Then we have 00, 01, 11, 10. Then 00, 01, 11, 10. So let me increase the length of this. So what you basically want to do is to fill up this with what you have here. So for this side, this is the AB side, and this is the CD side. So the first one is 0110. So wherever there's this intersection, wherever the intersection of this is already representing what you have here. So this 00 means A bar, B bar. This is A bar B. This is AB, and this is AB bar. The same thing here. So this is C bar, D bar, C bar D, CD, and CD bar. So this is 0101. So you look for where we have this intersection. This is 0101. So you write it 1 here. Then the next one is 101001, 1001. So this place also you write a 1. Then the next one is 0001, 0001. You write a 1. Then what's the next one? 0001, 1001, 1001, which is this. So you write it 1 here. Then 1100, 1100. So you write a 1. And then 1111, which is this. So from K-map representation, because all of this, everything in this row is 1. So we are taking the whole of this. So you represent everything here else as 0, 0, 0, 0, 0, 0, 0, 0, and 0. Yeah. So then for this part would be this, this first two, and then these two, like in two places, like individually. So for this first part, that is 1, the row representing this, the part representing this is CD. This is so this is C. I mean, the part representing this is 01. So which means this is C bar D. So it means our X. So this is the K map. This is the K map diagram. So so we're told to simplify it using this K map. So our work is not done because we have to simplify it. So this is going to be X. X now will now be equals to, this is 1, all of this is 1, so that will be C bar D, because the representation of what we have is the C. I mean, this is 01, which is C bar D. So then the next thing we now have is, for this one, we have 0010 under AB, right? So this is under this row, it is row, this is a row, yes. It is under this row AB, so that will be plus AB. Now, to be able to get this part, we look for, we are going to look for the, so we have under these two sections, we look for the ones that remains the same. What I mean by the ones that remain the same is we have 00 and 01. Zero and zero here is the same. It remains the same. It means C bar remains the same, while this second part, it changes. This is zero and this is one. So it means this would be AB C bar because C bar remains the same here. It's the static one here, not the D. So then the second one, for the second part, it is also AB. It is under AB. It's also AB. So for this second part, uh, 0, 1, C changes, but D remains the same. And because this D is 1, 1, it means it's going to be D, not the other one, it was the bar side that remains the same. But here, it is the D part, the 1, 1 that remains the same. So this is a simplification. So this is the result. This is the simplification using uh, K-map. So this is our answer. Do you have any question? Any question on this? Okay. Uh, is there any question?
Yeah, yeah. Hello.
Okay, I'm listening.
Yeah. How do you? I didn't get the way you get the final answer. This
The final
MP
answer.
plus.
Okay, okay. So let me
Yeah, F
re-explain
plus
now. Let me
C bar.
re-explain. You got the part of getting all of these simplifications right, like
Yes,
putting it in a K map, right? So
yes.
now,
Just the
after
answer.
yeah, after putting it in a K map, for this first one, this column, everything has one. Everything in this column has one. So since everything in this column has one, then it means CD. I mean, it means this part, we will write this part as a simplification. Like we would write this part, this particular column, which is 0, 1. And 0, 1 simply means it is this part. All of, assuming it is all of this row that is one now, it is going to be 1, 1, which is AB, right? But because it's this part, which is 0, 1, which is a CD side. So the 0 means C bar, then D. Assuming it is 1, 0 now, it will be C D bar. Did you get this first one now?
Yes, yes. I get
Okay.
it.
Now the second one, now we have 1, 1 because it is not all of it. So we'll have to make use of it 2, 2. That is in twos. So the first two now, this first one under this row is under row AB. So AB static, this AB, it is under row AB. So we are writing AB. Now to get the ones for this one, what we will do is it is under this and this now. It's under this and this. So we'll check the side that is static, that remains the same. That remains the same. So this is 0, 0 and 0, 1. 0 is still 0 here. 0, this one changes. The second part changes, which is 0, 1. So it means we are taking the part that remains the same, which is the C part. So 0 is bar. So that is what gave us the C bar. Did you get that?
Yes, I get it.
Oh,
Yes.
okay. Then the second one, same thing, AB, because it's still under row AB. AB, then 0, 1, the C side changes while the D remains the same, 1, 1. So that is why we now have ABD. Since it's 1, it is not going to be the bar, so it's ABD. So this is the simplification. C bar D plus AB, C bar plus ABD. Do you understand it now?
Yeah, I get it now.
Okay, good.
Thank
So
you.
yeah. So for the for the B 3B part, 3B. So 3B we are told to design a logic circuit that has three inputs A, B, and C. So it has input A, B, C. And uh so the we are told that the output will be high only when majority of the input is high. So let's make our output Q now, for example. So first we'll write the normal simplification, I mean the normal representation of this. So this is going to be 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 0, 1, one, one, zero, zero, one, zero, one, 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 zero, and then one, one, one. So we're told that the output, um, where's the question again? 3B, yeah, whose output will be high only. High means one. So when you hear high or low or true or false in computer, high is one, low is zero, false is zero, true is one. So that's like the Boolean representation in Boolean representation. So we are told that the output will be high only when the majority of the input is high. Since we are considering three inputs, it means that it is going to be high when at least two out of the three is high. That is, two out of the three has one, because we are considering majority. Assuming it's a two input system now, it will only be when either part is high. But because we are considering three, and we are told that majority of it, so it means this will be zero. This will be zero because it's only one part that is high, not two. So this will be zero. This will be one because majority of it, we have two that are high. This would be zero. This would be one. This would be one. And then this would be one. So now we have these parts. So the parts that are high, we have this, we have this, we have this, and then we have this. So it means so we are going to have, so X will now be, or Q will now be equals to, for this part, this will be A bar because the A side is zero. So A bar BC plus A bar BC plus the second one, A B bar C, then plus the third one, A I'm trying to see A B C bar, A B C bar, A B C bar, and then the last one is A B C. So um, we can simplify this further. So we can simplify this to be we can simplify this to we can simplify this to be uh, so A bar BC plus AB bar C plus AB into C bar plus C. Uh, so Q will be equals to A bar BC plus A bar C plus AB. Yes. I don't think there's any other simplification we can do here. Is there any other simplification? I don't think there's any other simplification we can do here. Trying to see this. There is actually. I'm trying to see. Uh, I'm trying to see if I get the simplification wrong coming because this is not the result I should get. Okay. Let me see. A bar BC plus ABC plus AB bar C plus ABC bar. Okay. So I'm canceling this. I'm bringing this last part to this first part so that we now have Q equals to BC into A plus A, then plus AB bar C plus ABC bar. So Q will be equals to A by A is 1. So this is BC plus AB bar C plus ABC bar. So I'm going to explain all of the Boolean expression. I think by the time we get to the next question, yes. So I'm going to I'm going to show us the Boolean, like what the Boolean algebras. So I think the next thing we can simplify here is BC. So this should be AB. So Q equals to AB bar C plus BC plus ABC bar. So this can be written as the second part. So the second part, which is this part, I can write this part, this second part as B into C plus AC bar. And from a normal Boolean expression of A plus A bar B equals to A plus B. So we are going to use the same I to represent this. So let me write this as AB bar C plus, yes. Okay, so this will now be, so this latter part would now be, so this is the same thing as writing C bar because this is A plus A bar, I mean A plus A bar B. So this is the same thing as writing C plus A or A plus C. That's the same thing that we have here. So that would be equals to AB bar C plus A plus C. That's, I mean, what we have inside. Yes, B into A plus C. What we have inside would be A plus C. So this will be equals to A bar BC plus AB plus AC. Then the final expression, the second part too, this second part, we'll do it the same way we did this. So that would be equals to factorizing A into B bar C plus B plus AC. So this is the same thing as equals to A,
Sorry, sorry, please. It's supposed to be BC, not AC. That last one.
that last one I'm coming, BC
AB plus AC. That last before
plus AC.
when you expanded, yes, it will be
Is
BC
it,
now.
oh, yeah, sorry, BC, sorry. Thank you. That's a lapse on my side. Thank you. Yeah. So this would be B plus C, just like we have here. So this is B plus C, then plus BC. So this will now be equals to AB plus AC plus BC. So this is the final simplification. and we are told to do like so this is not the final answer because we are told to draw we are told to draw a logic circuit of AB. So A dot B and so AND gate. Yeah. So then AC. This is supposed to be B. Sorry. So AC. Then the final one is DC. So for this A, so you can connect this to this. Since this is A, so this is the C. Then you connect this, this B to this, and then this C to this. I think there's a way David drew it in class instead, where you write ABC at the top and connect it. So, but the core goal is the core thing you want to do now is to make sure that the result of this, like every result of this, forms a what's it called now? Or gates. Don't mind my drawing, but yeah. So this is like the representation of your drawing. So it's the sum of products. Yes, sum of products of these three. Yeah, so that is the answer for that one. So the next one is 3C. Do we have questions? Do we have any question on that? Any question on that? Okay, there are no questions. So I'm hoping that we got that. So for 3C, we are told to simplify an expression. But before we simplify expression, I think I explained how to make it easier for you to be able to write out the formulas because you would need to know the exact Boolean expression you need to use when, especially when you are simplifying together. So we have 12 expressions. We have 12. Um, so A plus starts with A plus 0. Um, so we have 12 expressions. two out of it, the answer is 0. Two out of it, the answer is 1. Then a good part of the other ones are A. So we have A plus 0, we have A plus 1, A dot 0, A dot 1. We have A plus A plus A bar, A dot A dot A bar 9. Hmm, we have A dot, okay, okay. Then we have A bar bar. And then the 10th one is A plus B. Then the 11th one is A plus A bar B. Then the 12th one is A plus B, A plus B, A plus C, right? Yes, A plus B, A plus C. So we have all of this, trying to see if I'm right. A plus 1, A plus 0, A dot 1, A plus A bar, A dot A dot A bar, then A bar bar, then A plus B. Yes. So we have two that are zeros and we have two that are one. So for the ones that are zero, you know that for the ones that are zero, you know that A dot 0 is going to be 0. So that's the first one that is 0. Then the second one that is 0 is A dot A dot A bar. So this is the second one that is 0. Then the ones that are 1, A plus 1 is 1. Then A plus A bar is also 1. So the moment you know that a good number of the other ones are A, except for A plus A bar is A plus B. Then A plus B, A plus C is A plus BC. Then the other ones are A. This is A, this is A, this is A, this is A, and A. So the moment you know that, it will be easier for you to run your simplification. So for the first one, simplification is Z equals to A bar plus B into A plus B. So if you multiply, if you open this bracket, this is going to be A dot A bar plus A plus, A bar dot B plus AB, then plus BB. So from our simplification, A dot A bar, this would be 1 plus A bar B plus AB plus BB. BB is the same thing as AA. So BB would be B, right? So if we A dot B plus, if we factor B out, this would be B into A plus 1. Like if we factor B out in these two, we factor B out in these two. A plus 1 is 1. So that would mean we'll have A bar B plus B, since this has already turned 1. So if we factor B out again in A bar plus 1, I make a mistake somewhere. Okay, no. Okay. Let's factor B out. B instead. Factor B out. A bar plus A. sorry, A bar plus A plus B, yes. So factoring B out here would be A plus A bar is 1, so that would be B plus B. B plus B is the same thing as A plus A, so the answer is B. So this is our answer for this simplification. Then for the second one, which needs a little bit of like patience, but what you just need to know for this second one is that the final result you have to get is 1. The final representation of all of this is 1. So we have ABC plus AB bar B bar A bar B A bar B bar C, that's the third one, right? Plus A A bar A bar B C bar plus A B bar C plus A bar B bar C bar, then plus A bar B C for the second one. So for this one now, for the simplification, we want to simplify. So in simplifying this, the first thing is how many is this? One, two, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. I've not completed it. A, B, C, A bar B, C, A, A, B bar C, A bar B, C bar, A, B bar C, A, B bar C, then, okay, I think I missed out. After A, B bar C, I missed out A, B, C bar, then plus A bar B, C. Yes, okay. So I think we are good. Everything is everything is complete. So the first thing is I want to move this first one, and I want to move this first one and this sixth one together. So A B C plus 1, 2, 3, 4, 5, 6 A B C bar. So I want to move them together. Then I want to move this. So this one is out. Let me just clear the one. So I move this and the sixth one. 1, 2, 3, 4, 5, 6. Okay. And the sixth one. So I want to move AB bar. Which other one has AB bar? Okay. I want to move this and this and this also together. These two. So the second, so the second one, which is A, okay, let me just arrange them together, plus AB bar, AB bar C bar, plus AB bar C. Then we have this A bar B C bar and this. So this and this together. So uh, so we have A, which one did I cancel now? Okay, this middle one. A bar B C bar plus A bar B C, right? So we are now left with these two. So plus A bar B bar C plus A bar B bar C bar. Yes. So we've been able to rearrange everything to make it easier and simpler for us. So this is the same thing as AB into C plus C bar plus these two together, AB bar C bar plus C plus we've done this for A bar 1, 2, 3, 4, A bar B into C bar plus C. Then the last one plus AB bar C plus C bar. So all of this is one. This will be one. This will be one. This will be one, and this will be one. So we have AB plus AB plus A bar B plus A bar B bar. Um, A AB plus AB is the same thing as A plus A. So this will simplify as AB plus, like these two together is just like when you have A plus A. So that will be AB. So then this is A bar into B plus B bar. So this will be equals to AB plus A bar. I think I've made a mistake somewhere. Uh, I made a mistake somewhere. Okay, this is AB. This is supposed to be AB bar, right? A bar. Yeah. Okay. Yeah. This is supposed to be AB bar. AB plus AB bar. A bar B plus A bar B bar. Okay. So this is A into B plus B bar. Then plus A bar into B plus B bar. Yep. So this is equals to A, because this will be 1, A plus A bar, because this will also be 1. So A plus A bar from this knowledge equals to 1. So the whole simplification of that is equals to 1. So that's the result of that. It's equals to 1. Did we get this simplification? Did we get this? Any question? Any question on this part? Any question on this part? Okay, I'm taking that as we understand that part. So the next part is, I think I have like 30 minutes more that I want you to explain. I have a meeting. So the next one is question 4. Question 4A states that a circuit has a circuit has 4 inputs. It has a 4 input. It has 4 inputs A, B, C, D, encoded in 8421 natural binary form. For the inputs is in the range of 0000 to 1001, whatever, representing month of the year from January to December. Inputs in the range of 1100 to 111 cannot occur. The output of the circuit is logic 1 if the month represents input as 31 days, otherwise it is false. So we are told to draw a truth table for this. So first A, B, C, and D. Then we have our output. For our output, let's write months. Then our output. So zero, 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 one, zero, zero, one, zero, 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 one, one, zero, one, zero, 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 one, zero, one, zero, one, one, zero, zero, one, 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 zero, 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 one, zero, zero, one, one, zero, one, zero, one, zero, one, 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 zero, zero, one, one, zero, one, 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 zero, one, 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 one. Okay, good. So we're told that each one represents the month of the year. So this is January, then February, March, April, May, June, July, August, September, October, November, December. And remember that we were told that inputs in the range of 1100 to 111 cannot occur. It means all of this would not occur. That is, they are invalid, 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 invalid. So for our output, we're told that the output only gives a 1 for months that are 31 days. Months that are 31 days in a year are January, March, um, May, July, September, no, October. It's August 31 days. August is not, it's August 31 days. Okay, August is 31 days. Wait, let me confirm from calendar first. Okay, yeah, August is 31 days. July, August, October, and then December. So these are the only months that would impute um, these are the only months that would impute 1 or that will return 1, because we're told in the questions that output of the circuit is logic 1 if the month is represented by inputs as 31 days. So it means for January, January 1, this would be 0. This would be March 1, April 0, May 1. No, May is 30 days.
No, May is 31 days. Oh,
Okay, May is 31. Sorry. Yeah. Okay, May is 31. Okay, yeah. May is 31. June 0, July 1, August 1, September 0, October 1, November 0, December 1. So we are not done. So from the truth table, use Boolean algebra technique to obtain a simplified expression for this. So after we've gotten these results, the next thing we want to do is now to create the Boolean expression. So Q equals to 1, 0, 0, 0, 0. So that will be A bar, B bar, C bar, D bar plus. The next place we have 1. So we have 1 here. We have 1 here. We have 1 here, 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 and here. Yeah. So yeah. So the next one is match, which is A bar, B bar, C, D bar. Then plus the next one is May, A bar, B, C bar, D bar. Then the next month is July, A bar, B, C, D bar. Right? Yeah, July. Then plus August, A bar, B, C, D. Then October, A, B, B bar, A, B bar, C bar, D. That's October. Then December, A, B bar, C, D. Okay. Now we have this is our result. So we want to simplify this. This is how many? 1, 2, 3, 4, 5, 6, 7. So we have 7. So we want to simplify this result. So we want to move similar things together. Let's see. Sorry. Okay, we can move this and this together. This, this, and this. So um, Q would be equals to A, A bar, B bar, C bar, D bar plus A bar, B, C bar, D bar. Okay. So which other parts can we move together? A bar, B bar, A, B, C. Yeah, we can move these two also together. We can move these two together. So that will be A, B bar, C bar, D plus A, B bar, C, D. So we've eliminated this and we've eliminated this. So which other one? We can move this and this together. So that is A A bar, B bar, C, D bar, yeah, plus A bar, B, C, D bar. Yes. So we eliminated this and this. Then the leftover would be A bar, B, C, D. So I think this makes it easier for us now to calculate. So this is the same thing as A bar, B bar, uh, B bar, C. Okay, this is the same thing as C bar, D bar into B bar plus B. That's the first one. Plus, we can move out ABD here. A B bar, AB bar D, AB bar D. So we have C bar plus C. Then for this one, we can move A bar C D bar. First one, second one, yeah. Okay. A bar, A bar, uh, C D bar into D plus B bar plus B, then plus A bar B C D. So our Q would be equals to A bar C bar D bar plus A B bar D plus A bar C D bar plus A bar B C D. So for that simplification of this, we can simplify this and this now. So Q equals to A, so I'm just going to move them together first, plus A bar C D bar plus A B bar D plus A bar B C D. So Q equals to A bar D bar into C bar plus C, then plus A B D bar plus A bar B C D. So Q, so we have A bar D plus what else can we simplify? Should be one more thing to simplify. Okay, there's nothing else. I think this is like the last simplification. So A bar D bar plus A B D plus A bar B C D. So this is our final answer. Then we are then to construct a circuit to implement the function AND gates, using AND gates, OR gates, and um, AND gates, OR gates, and NOT gates. So for this, we are going to have A, B, C, D. So we want to draw a circuit. So the first one, for the first one, it is A, D. It is A and D. So the diagram would be like this: A, So uh, A and D. But for A, because it is A bar, and we are told to make use of NOT gates and gates for all. So we are going to, so NOT gate is just, they put a NOT gate here. Yeah, so NOT gate is just the inversion of A. So it's just anywhere you have the bar. For example, we have A bar now. So we are going to represent it with a NOT gate. So, so this is the hand of these two bar. Where's hand? So this is the hand of the two. There to be a, it's to be a straight line, no, but because I'm implementing, because I'm trying to manipulate this design, that's why I'm drawing it like this. So AD will be like this, A bar, because it is, so it's going to be north of A and this. So the second one is ABD. So B bar. So it means for our B, we are going to make the our B not dead, not gate. Then D. So this would be the hand of these three. The hand that I have here is two inputs, but the way it's supposed to be is going to be the three input goes into this hand. Then the third one is not of A, then BCD. So the same thing. Um, A naught, I can take this output since this one is already the knot of A, or you can draw the knot directly. But let me just take this. I don't need to invert this because this is an output of A naught already. That's why I'm not inverting this. I'm taking the output of A naught already, then BCD. So um, B. So the hand of these four, of these four, then you are now to combine these three as an OR gate. So the output of all these three will come out as an OR gate. Like the output of all of this would now link to this. So this is this is what your cycle should look like, something like this. But you have to make sure that you implement this NOT gate because we are told to construct it using an AND gate, OR gate, and a NOT gate. So for SR slash, I mean SR latch is I'm just about to read this part, but SR latch is a set and reset latch. It's a type of it's a type of latch, right? So, but I think for these ones, for these questions, I don't know it yet. I will probably have to check. I will probably have to check it over this night and tomorrow before the exam. But for these ones, you have to answer it using a function table and a circuit diagram. So you want to make sure that you draw the circuit diagram for this one. So let me move to. I don't think we have any questions regarding this, right? Do we have questions regarding this one? Okay, I'm taking it that we don't have a question. So 5A, 5A is just using one's complement. So we were told to subtract 1101 base 2 from um, from 11011. So it simply subtracts this from this, right? So in one's complement, please give me a few minutes. Hello, ma'am. Yes, ma'am. Ẹ kalẹ̀ mọ́. Mo ń gbọ́ yín mà, mo ń gbọ́ yín mà. Ok, mo máa béèrè lọ́wọ́ ẹ̀, mo ń ṣe nǹkan lọ́wọ́ tí má ti ṣe tán mo máa béèrè lọ́wọ́ ẹ̀ mọ́. Yes. Ok. Mo ń ṣe class kan lọ́wọ́ tí má ti ṣe tán mo máa bá a ṣílẹ̀kùn. Ń bọ̀ mọ́. Yes. Ma'am. Yeah, sorry. So you have to subtract this, subtract this one, the second part from this. So it's going to be like this. So in one's complement, it is going to be the opposite of everything that you have here. By sorry. So in one's complement, the number we want to subtract from this is 0011. So we are going to write this in the inverted form. By inverted form, it means where we have 0, it will be 1, and where we have 1, it will be 0. That is the subtractor. I mean, what we want to subtract, what we want to use to subtract the first one. So it means this, instead of 01101, it will now be 10010. So this is what we are going to have. Now, when you now have this, the next thing you now do is you are now going to add. I know it's a subtraction, but you are going to add. That is how you get your answer. So you are going to add this. So we have 1. 1 plus 1 is 10. So that will be 0. That will be 0, carry 1. Carry 1 here. So it means this will be 1. Then this would be 1. This plus this is 1. This plus this is 10. 0, 1. And we have that 1 here. 1 plus 0 is 1. Then 1 plus 1 is going to be 10. So we have 1, 0. So this is going to be what your result will be. So after you've now gotten this, you are now going to carry this one. You're going to carry this one. You're going to carry this one, and you are going to, so this leftmost, this is left, yes. This leftmost bit, you are going to add it to this result that you got, like this whole result, this result that you've gotten. You are now going to add this one to it. So if I add 1 to this, if I add 1 to this now, if I add 1 to this, would be, this will give me 0, 1, 0, 1, and then 1, 1, 0. Yeah. So I added this one here. So this is going to be 1. And this is going to be 10. Bringing this one here, this will be 1, then 1, 1, then this is 0. So this is going to be the answer of this one's complement. So when you are doing one's complement, the first thing you do is the number you are subtracting, you are using to subtract, you invert it. That is, you change from, if it is 1, it will be 0. If it is 0, it will be 1. So after you've done this, the next thing you now do is you now add this. You do an addition. You do an addition. So when you've done the addition, if you now have a carry of 1, if you have this 1, you are going to remove this 1 from here. If it is 0, you don't need to remove. But if it is 1, you are going to remove this 1 and add it to what you have here. Since you've removed it, so you add it, and then this will now be your answer. This will be your answer. So I have less than 5 minutes. I have a class. I have a meeting. So let me just explain the others. Code the decimal number 552. 522. Code it in binary and hexadecimal. So this is going to be divided by 2. This one will be divided by 2. So you want to divide 552 by 2. We know how to do binary. We know how to do binary. Um, we know how to do binary division, right? I'm guessing that we know how to do it. So I'm just going to. So 2. The first one is binary. So 2. So you are dividing this by 2. So when you divide this, you get the result 0, 0 something. Then for hexadecimal, you divide by 16, and then you get the result for, that is AII. You get the results for this, or the result you are going to get here. You necessarily don't need to divide for the hexadecimal. The result you get here, you can now divide it into bits of 4s. You can divide it into bit of 4, the same way we did. Like after you've gotten your binary number, whatever it is, you can now do it the way we did. Where's this part now? Yeah, you can now batch it into 4. Then whatever you get would now be the hexadecimal representation of your results. Would be the hexadecimal representation of your results. Then for 5B, our computer is transmitting 8 bits. So this is 8-bit transmission. So 8-bit transmission is 8 bits. So it means 8 of this. So 8 of this. So you are going to give the equivalent in octadecimal and in hexadecimal. So 3, 3. If it is octadecimal, it will be in grouping of 3. So this will be 3, 3, and 3. In grouping of 3, sure. So each one grouping of 3. So let me just do an example. So this is 1001100. So for the octadecimal, this will be in grouping of 3. So let me write it again. Okay. So 1001100. So in grouping of 3, 3, and 3. So this is the octadecimal representation, and the hexadecimal will be in grouping of 4, the same way it is 1100. Then you write the equivalent result. So that is how you would do for each one that you have here, like individuals, each individuals. Then we are told to prove the Boolean identity that this we are told to prove that this is equals to this. So we are going to use Boolean, I mean, our, we are going to do, this is, so we want to prove that the right hand side, I mean, the left hand side equals to the right hand side. So this part is A plus B into A plus C. So we want to prove that that's the answer. This, if you multiply this, this would be A dot A plus A dot C plus AB plus BC. So A dot A is A from our, what's it called? From our Boolean algebra, whatever. So we have A plus AC plus AB plus BC. So we can factor out A here and have C plus 1 plus AB plus BC. So C plus 1 is the same thing as A plus 1, which is A. This would be A. I mean, which is 1 rather, which is 1. So it means C plus 1 is 1. So this is A plus AB plus BC. So this will now be equals to, same thing, factor out A into 1 plus B plus BC. So this is equals to, this is 1, A plus BC. So now you now say that it shows that the left hand side is equal to the right hand side, since this is also equal to what you have there. So you do the same thing for this one too. You do a simplification, and then you, okay, for this second one, it's a simplification. So you want to simplify this to like the lowest form, just like what we did, what we've been doing before. So this would be AB dot AB plus ABC, then plus ABD. So so this would be AB plus AB is AB, just that like A dot A. A dot A is A dot A is A. So this is AB plus ABC plus ABD. So this is AB into 1 plus C plus ABD. This is 1, so that's AB plus ABD. So this is equals to AB into 1 plus D. So our answer is equals to AB. So the simplification of this is AB. Then you do also for this one too. You simplify it. So I have a class right now. For this one, it is De Morgan's theorem. You can check the class notes. Plus, I think David also. I think I'm going to. David will share the notes that he answered it in his on the group, so you can see this one. Then for this one, it's just the same thing, proving the Boolean algebra. You simplify it. You break the bracket and try to break it to like the lowest form. So explain the following. SOP is sum of products. So it's just the sum of products. It's what we've been doing here. It's the sum of different products. This is a product. AB is a product plus AC plus say BC. This is the sum of products. So, and there are two types of SOP. There is non-canonical, non-canonical sum of product and canonical sum of products. So, canonical sum of products is the standard, this standard SOP form. So, I think it's the one that has all of the function. Let's say if we say QF comma A now, in your representation, in your sum of products, F and A are duly represented. So I think probably if you read note on it, you would get that. K-map is the visual representation of your Boolean expression, just like what we did here, K-map. So, I mean, cannot map rather. So, cannot map. Then explain flip-flop. So, flip-flop, earlier on, we talked about combinational logic circuits. Combinational logic circuits, they have no memory, remember. They are dependent on the what's it called now? They are dependent on the inputs. The output you will get is dependent on the inputs. But for flip-flop is like they call them sequential circuits, but it's like a memory now added to a combinational circuit. So you have a memory. So it means for flip-flop, it has a memory that retains the previous information that you have. So that's flip-flop. But flip-flop and latch, they are closely the same, but there is a difference between them. I'm trying to see. Uh, I'm trying to see where it is. Okay, so there's a difference between them. The difference is that flip-flop is edge triggered, and I think latch is clock triggered. It's based on clock sequence or whatever. But if you read it, this part I've actually not read it in detail. So, but if you read it, you will get it. Then the same thing falls into clock signals, JK flip flop explanation. Then for this part, we are going to draw, and so I think a good number of all of these are drawings and explanation, and also this one. For this one, I'm going to share, I think I saw a resources on this, the drawing from this. I'm just going to share. I saw two resources that I think I'm going to use. A particular textbook that is used, digital logic that is used for tutor, is a old textbook, so you probably just search out this particular part to get the actual drawing. So I'm going to send it to the group for all of these remaining parts. But I think for the other parts, I think we should be good. And I'm hoping that we'll not have surprises. We'll not have surprises in the exam the same way we had surprise in the test. And I'm hoping that at least with what we've treated here, we'll at least be able to answer out of the four, would solidly be able to answer two or three out of the four. And hopefully we'll be able to read up on the remaining parts. Does anyone have any question? Does anyone have any question before we close up here? So I am going to end this. I don't think anyone wants to rewatch this. Does anyone want to rewatch this? I'm recording it, but I don't know if anyone wants to rewatch this. Let me
Yes,
see.
there's someone that wants to rewatch it.
Yes, please.
Okay,
Yes.
Yes.
all right. Okay, so I will I will drop it on